Okay. So in my talk today, I will start with a short introduction. I will talk a little bit about the additive manufacturing methodology. I will show some previous results on mechanical properties, tensile properties, and fracture toughness properties of this material. Then I will show you some results on the lattice structures that we manufactured, and finally I will draw some conclusions. So polymers are among the most used synthetic materials in modern applications, and because of their good mechanical properties, lightweight, low cost, they are used more and more in many applications. In our region in Timișoara now, there are a lot of car manufacturing components, and they are trying to replace aluminum mostly with some polymeric materials. From the point of view of manufacturing, so they can be easily printed using different technologies, using additive manufacturing methods. So we use VAT photopolymerization. This technique, for this technique, the liquid resin is in a liquid stage firstly, and then it's stay in a vat, and then is selectively sinterized, solidified by either by a moving laser, which produce an ultraviolet light, or by a digital light processing. So usually it's a LCD used, and this solidifies one layer at one shot. This technique has some advantages. It's very fast, has a very good resolution, allow multi-material to be applied. However, there are some disadvantages. The components obtained through this technique needs a post-treatment. Actually, manipulation of liquid resin should be made with care. It's toxically, and this is the reason that needs some expert user to manipulate. So we use a commercial 3D printer. So the technology is DLP, digital light processing, using a source as a source light LED with 405 nanometers length and power of 25 watts. The volume, the building volume is not so big. It's around 100 millimeters or less. This is the reason that we were somehow constrained on the dimensions of our specimens. Has a very good resolution, 47 microns. The layer thickness is between 0.01 to 0.2 millimeters. The printing speed is up to 20 millimeters per hour, and the resin, it's a commercial resin for this printer. Our first results were in tensile, where we play with different manufacturing parameters. We varied here layer thickness, exposure time, spatial orientation, cleaning and curing post-treatment. I will show you only some results, so the engineering stress strain curve for this, and then the tensile strength results versus exposure time and layer thickness, what we can see, and we expect this. So the tensile strength increasing with increasing the exposure time. This can cause longer manufacturing time, and also lower layer thickness gives higher tensile strength. Going to the mode 1 fracture toughness results. So here we consider 3 post-treatment regimes, cleaning in isopropylic alcohol and for 5 minutes, and 5 minutes exposure to ultraviolet light. cleaning in hot water, 60, 70 degrees Celsius, and ultrasonic curing, and 5 minutes cleaning in isopropylic alcohol and ultrasonic curing. Then we keep the first treatment, so 5 millimeters, because this gives the best results on fracture toughness. 5 minutes in isopropylic alcohol and curing for 5 minutes in ultraviolet light, and we change the position of the specimens, 0 degree in plane of the vat, then 90 degree perpendicular, and 45 degree. The result, so we follow the standard ASTM 5045 standard. We use single edge notch bend specimens loaded in 3-point bending. We did the test at room temperature with 2 millimeters per minute. These are the dimensions of the specimens. We use the classical relations, the standard relation for determining the fracture toughness. These are some results. So, for example, looking on the post-curing treatment, the highest fracture toughness, which is 1.3 megapascal square meter, were obtained for cleaning in isopropylic alcohol and then ultraviolet curing. The other two regimes give lower fracture toughness. Regarding the spatial orientation, so the highest fracture toughness was obtained in plane. So we directly manufacturing the notch on our specimens. So, and here the notch is perpendicular to the layers, while for 90 degree the notch is in the plane of the layers, and this is the reason that the lower fracture toughness was obtained for 90 degree orientation, which is 0.38 megapascal square meters, and there are quite high differences between the treatments and also between the spatial orientations. We check all the tests, fulfill the plane strain condition for this case, so this material it's quite brittle. Then, talking about lattice structures, these structures are lightweight, periodic, or stochastic framework. They are made of struts, beams, or surfaces, and they are more and more used in aerospace engineering, in biomedical, implants, automotive, and so on. So they have high strength to weight ratio. They have excellent energy absorption property. They can be used to tailor the mechanical properties. They are easily obtained now with additive manufacturing. Design is very flexible now. They have potential for cost savings, and also we can reach multi-graded or multifunctional structures using this type of materials. So we consider two, let's say, well-known use lattice structures: the square one, so the triangle one, and the third one we try to use a bio-inspired one. So we have 60 by 60 millimeters width and 15 millimeters thickness. The strut thickness was 0.6 millimeters. So the third structure that we consider, it's a deep sea sponge. These kind of structures is in the deep sea from millions of years. They have very good mechanical properties. Even they are some microorganisms. They look very fragile, but they have very good mechanical properties. So, inspiring from this, we built a model for this kind of let's say sponge-inspired lattice structure. So the manufacturing parameters, we print all of them in the plane of VIT. So orientation was 0 degree. We use 0.05 layer thickness. Exposure time was decreased because time takes a lot if we go for a higher exposure time. And we use the best let's say, post-curing treatment that we get the results from the fracture toughness test. We did compression tests. We use our machine from our lab, the thick ProLine testing machine. We did the test at room temperature with a loading speed of 5 millimeters per minute. These are some comparison between these three structures. So what we can see here, the lowest energy, considering the energy, the area below the low displacement curve, is from the square structure. Then we have higher for the triangular, and we can get this, let's say, typical low displacement curve where we have a plateau for the cellular materials, and the third one is the sponge-inspired structure. So I hope this will work. If not, I will ask Francesco to help me to click on the images, on the first one, please. I hope are working this. Only a click on the image, if it's possible.
I don't know, because
probably it's in it's okay now. So for the rectangular structure, so we have buckling and then failure of the let's say lower layer. For the triangular, we have a local buckling on the edge and then fracture. For the sponge structure, we have no buckling at all, and the failure is at 45 degree band. So having this, let's say, experimental results, we move to try to simulate the behavior. So we use compression, we simulate the compression test, the buckling for the square specimen. Then so we use ANSYS, we block the displacement down, and we impose a displacement on the top of the edge. So this is compression test, and this is the buckling test, where you can see we have local buckling on the edge of the specimen. And sorry, this is the sponge-like structure where there are no buckling, and the failure is at 45 degrees, the struts on the 45-degree orientation, so this band of deformation are broken. So what we try, taking the load from these simulations to compare with our experimental values. I forgot to say, for each test, we use at least four specimens. What we can see here for triangle, we are very close. So the experimental data are these which have the error bar. The other are the simulations. So what we get the load which correspond to the maximum principal stress, or when we reach the maximum principal stress. The lower values here are the buckling. So the buckling is not the main, it's the first step in damage of these structures, and then either bending or stretching of the struts cause the final fracture. So what we also try to see the specific strength, so is the strength of the structure divided by the density of the structure, and we relate this to the specific to the relative density of the foam. So is the density of the structure divided to the density of the solid materials. For this, we build some blocks and we determine the density for this. We measure them and we weight them. And this was let's say the density of the solid material. So, and then we try to apply some let's say criteria or models given by Gibson-Ashby as known as micromechanical models. So we try to predict or to compare our Young modulus and tensile strength of the structure with these models. So for Young modulus, the stretching and the bending relations are given like this. So is the ratio between Young modulus of the structure and Young modulus of the solid materials. Usually it's a constant multiplied by the relative density at power m. What we can see from this and from our test, so these are experimental, these points are experimental data, these are the curve given by these models, that the stretching model is the closest to our Young modulus results. The bending one it's quite far. So this means that after the buckling for the first two structures, we have stretching of the struts and breaking of the struts by stretching. So then we use the same model for stretching to predict the tensile strength. So the tensile strength is between these coefficients 0.4 to 1 multiplied by relative density at power 1.5. So we only check against this. We didn't try to come with another micromechanical model from here. So to conclude, so there are many parameters which are influencing the properties of the additive manufactured components: exposure time, layer thickness, specimen orientation, post-processing, treatment. All have a very high impact on this. Looking on the fracture toughness, so this ranges from 1.3 to 0.38 megapascal square meters, depending on the manufacturing parameters. What we observe that the sponge structure, which is a bio-inspired lattice structure, has the best relative strength, and we validate some micromechanical models to describe the Young modulus and tensile strength of these materials. What we want to go further, we want to analyze locally what's happened, to apply the strain energy density approach, because we have, in particular for this structure, we have different angles here, 90 degree, 45 degree here, 135 degree, we have, and 90 degree here, and we want to apply the strain energy density. What we need more experimental data to have the tensile strength and the fracture toughness determined on the same conditions of the manufacturing of the lattice structure. We are running now another set of tests with another resin, and we also employ the digital image correlation for this. So thank you very much for your attention.